So, thank you for inviting me to this very nice semester. So here I'm going to talk about something I call Brownian surfaces, and more precisely geodesics in these random metric spaces. So I'm going to explain that in a moment. So I will first start with recalling what Jason just explained 1 hour ago about the Brownian map. Sorry. Oh, does it work? Does it work? Yeah. Okay. So I'm going to recall the story about the Brownian map in a few slides. So first, recall that the plane map is what Jason just explained. It's a connected embedded graph in the sphere, and it's it would be very useful to consider actually routine maps, meaning that one of the oriented edge is distinguished and called the root. Okay, and these guys are considered up to edge deformation. So maybe another way to see the maps is to see them as the gluing of polygons, you glue polygons along the edges, and you obtain the sphere. Okay, so the main result is, of course, the following. That's the one Jason just recalled. It is due to Jean-François Le Gall and Grégory Mirmont, two different proofs about the same time. So the theorem is precisely the following. You take so I call Qn a uniform plane quadrangulation with n faces. So recall that quadrangulation means that all the faces have 4 edges. So if you want, you glue squares together. And if you look at you see them as metric spaces by finite metric spaces by endowing the vertex set that I will call V of the map with the graph metric. The distance between two vertices is just the smallest number of edges you have to cross to go from one edge to the other. And if you rescale by this factor, so it's roughly n to the minus 1/4. So there is a 9 over n that's not really important here. So, well, this sequence of random metric spaces, it converges in the sense of the Gromov-Hausdorff topology toward a random compact metric space we call the Brownian map. And if you don't really know what converging in sense of the Gromov-Hausdorff topology means, it just means that you can isometrically embed all your metric spaces into the same common metric space in such a way that in this common metric space you have convergence for the Hausdorff topology. And recall that the Hausdorff distance between two compact metric space is just the smallest epsilon you have to add to each set to contain the other one. So okay, so that's the main theorem about random plane maps or planar maps. And what I'm going to be interested in this talk is to generalize this theorem to more general surfaces. So this plane, the plane here means that the maps are maps of the sphere, and I'm going to look at other surfaces and similar results for other surfaces. So somehow the Brownian map is the first Brownian surface, and in this case the surface in question is the sphere. So okay, so recall that first I will need surfaces with a boundary. A surface with a boundary is well, there is a well-known classification theorem telling you that it's basically just a connected sum of tori with a disk removed. So here, for example, you have one torus with 3 disks removed. The surface of genus, the genus is the number of tori. So if G is 0, it's the sphere. If G is 1, it's the torus. G is 2, the double torus, and so on. And I will denote by P the number of holes, so the number of disks I remove from the surface. So okay, so I'm going to consider maps of these surfaces. So it's always here. It's always orientable surface. Okay. So Gregory just introduced very briefly in his first lectures, I think, the maps on arbitrary surfaces. But as nobody talked about it, I will recall the definition. So you have a graph embedded in a surface here. So right now I don't have any holes. So it's just either the sphere or the torus, the double torus, and so on. And I embed the graph, but I really want the graph to be somehow embedded as best as possible, in the sense that I want all the faces to be topological disks. So really, it's here again, it's a gluing of polygons along the edges in such a way that you obtain the surface you want. So either the torus, once again, or double torus, and so on. Okay? So that's the definition of a map of genus G. And here the definition is a bit trickier, because the edge deformation the deformation of the edges we are allowed to do is actually a bit more complicated, because the proper way to do things is to consider maps up to homeomorphisms of the underlying surface. So for example, here I draw through two embedded graphs on the torus, and I'm claiming that that's the same map. And of course you cannot just deform the edges to go from here to there, but what you can do, if you want to go from here to there, actually you take your torus, you cut at the rear, you make one turn in this sense, and you glue it back. So that's a homeomorphism of the torus. It's called a Dan twist. And when you do that, see that the edge here that was straight, you actually wind it, and it goes around the back here. And the one that was making a wind here, you actually unwind it when you glue back. So that's really the same map. Okay. So you just have to bear in mind that the identifications are a bit trickier, but so in the end, the real definition of a map is it's an equivalence class of embedded graphs in the surface for this equivalence relation. Okay. Okay. So how about boundaries? So far, I don't have any boundaries, and so what I really want to consider is quadrangulations with holes. What I call a quadrangulation with p holes is a map embedded in some surface of some genus without holes, and with p distinguished faces that I will call holes. So, okay, and I actually want all the faces that are not the holes to have degree 4. So really, you have faces of degree 4 plus p faces of arbitrary degree called the holes. And in red, I added a little extra condition. I want my maps to be bipartite, which means that you can color all the vertices in black and white in such a way that no edge links a black vertex to a white vertex. So that's a technical issue, and you will see why it appears. But so far we have to do that in order for what I'm going to explain work. Okay. And so see that when the map is bipartite, because when you go around a hole, you will see a black, white. So actually the holes are necessarily of even degree. So if I take just a p-opal, sigma 1, sigma p of integers, I can consider the set q and sigma of quadrangulation with n faces when n squares, and p holes of degree 2 sigma 1, 2 sigma 2, 2 sigma p. And well, actually, the genus of the surface, I didn't put it in the notation here, but the genus will be always fixed in the whole talk. Okay. So you see maybe at this point that that's a bit weird that I first defined the surfaces with a boundary, and then I said that a quadrangulation with holes is embedded in the surface without a boundary. But the reason is because of this picture. So this, for example, is a quadrangulation of the torus with 3 holes, 1, 2, 3, and see that the hole H1, the boundary of the hole is not a simple curve. So if I just remove the holes out of the surface, I don't get a surface with a boundary, because the boundary of the holes have to be simple curves. And so in this case, I cannot just say that if I remove the faces, I have a surface with a boundary. So that's why I chose to make this, to use this definition. But of course, if you just remove a small disk inside every hole, you have a surface with a boundary. Okay? So you can check, for example, that this map has 19 square faces, or you can believe me. Okay, so these are the objects I'm going to consider. And here you can see that I rooted at some oriented edge. Okay, good. So the first result is the following. So it's basically a weak version of the first result I recalled by Jean-François Le Gall and Grégory Miremont, which says that, okay, so you want to look at the scaling limit of maps like this. So what you want to do is to let the number of faces tend to infinity. But when you do that, of course, you have to say you have to prescribe the length of the boundary. You cannot just say, I take a uniform quadrangulation with p holes and faces if you don't say how you have to put a condition on the size of the holes. So the way that works is actually to consider holes of length of order the square root of the number of faces. So more precisely, you fix once and for all the number of holes. The genus is also fixed. And you consider p sequences of integers, sigma n1, sigma np. And you want these sequences to be equivalent to a finite positive number times square root of 2n, which are called sigma I infinity. And then, once this is fixed, you take a uniform quadrangulation with n square faces and p holes, the first hole of size 2 sigma n1, and so on, and the p hole with length 2 sigma np. So that gives you a metric space with the same identification as before. You just consider the vertices, and you end out that with the graph metric. So the result is that this sequence of metric spaces, so far it doesn't converge to something, but you can extract subsequences along which you have convergence. So of course, in the case, if you look at this setting in the case p equals 0 and g equals 0, that's just a sphere. That's a theorem of Jean-François Le Gall dating 2007. And actually, that was the first step, if you recall Grégory's lecture, that was the first step to show the convergence toward the Brownian map. And so, of course, the question is, do we have the full convergence, or do we only have subsequential convergence? And the answer is yes. We also have the full convergence. And so you all know that this is a theorem of Jean-François Le Gall and Grégory Miremont in the case of the sphere. And in the general case, this is a joint work in progress with Grégory Miremont. So the result is what you expect. You still fix your sequences of boundary length. You take a uniform quadrangulation with n internal faces, and the prescribed boundary length, and then this sequence of random metric spaces converges without any extraction toward something, toward a compact random metric space. And this guy here is what I will call a Brownian surface. Decided to state both theorems. Of course, this one is stronger than the previous one, because what I'm going to say now does actually not need this theorem. We only need the weak version of the theorem to keep up. Okay, so the limiting space, as I said, will be called the Brownian surface, and more precisely, you have to replace the word surface with the surface you are considering. So if you consider maps of the torus, you will have the Brownian torus, you have the Brownian disk, the Brownian cylinder, of course the Brownian pair of pens, and the first theorem is that I'm allowed to do that because actually the topology of the Brownian surface is the right topology. So so the Brownian torus is actually a torus, the Brownian cylinder is a cylinder, and so on. Okay? So yeah, I didn't say it, but of course this theorem for the Brownian map is due to Jean-François Le Gall and Frédéric Paulin in 2008, and also to Grégory Mirmont 2008 with an alternate proof. And also the Hausdorff dimension of any Brownian surface is, as you already know for the Brownian map, is always 4. But maybe what's new here is that the Hausdorff dimension of the boundary of every boundary component actually is almost only 2. And so here again for the sphere, I forgot to mention it, but it's a result due to Jean-François Le Gall in the previous paper of 2007. Okay. All right. So these are the main properties of the Brownian surfaces. And okay, I will just finish this section by showing you some nice pictures. So that's actually almost the same picture as the one Jason just showed by Jean-François Mercœur. This is a uniform quadrangulation of the sphere. But here maybe you can see the sphere a little better because it's in 3D and all. Okay, so that's quadrangulation with 50,000 faces, and of course you can do the same for any surface. So that's, for example, a double torus. You can see the 2 handles. So that's a quadrangulation of the double torus with 30,000 faces. And if you are bored, you can always go to my webpage and look at these computer simulations. So that's a bit longer too. So, for example, this one is a double torus and with 2 boundaries. So this, for example, the blue line here is 1 boundary, and there is another right here. And well, if you look closely, you can see the 2 handles. Okay. No, no. This took about maybe 5 to 6 hours to generate one of these with this number of faces. No, of course not. Okay. Okay. So, well, if you were here the last couple of weeks, you know that the first step to show this result is to use a bijection, the so-called Corriveau-Klein-Schaeffer bijection. Well, in general, it's there is also a bijection that allows you to encode your maps by some simpler objects. So, if you remember, in the case of the Brownian map, the simple object encoding the Brownian map was what we call the well-labeled tree, so a tree with labels. In general, it's a bit more complicated, but the bijections are always using the same technique. And so let me explain the bijection on an example. So here you have a plane quadrangulation with 3 holes. And the idea is to do that. You first select a vertex, this one, for example, And then you label all your vertices by the distance between your vertex and the selected vertex. So for example, this vertex has label 3 because it's at distance 3 from the red vertex. So that's the first thing to do. And then you just apply a rule, and the rule is the following one. So, and there is a rule depending of your face. If it's an internal face, there is a rule telling you to add an extra edge inside the face. And if it's an external face, the rule tells you to add actually a pink face like that. So I'm not going to enter into details here because I don't have time. But well, there is a rule telling you what to do. So you do that. And then you remove the edges you started with. And well, you obtain something. And the something you obtain is actually a new map, a label map. You have labels on the vertices. And as you can see on this picture, it actually has 3 holes and 1 other face. And so there is an obvious bijection between the holes you started with and the new holes, because the rule told you to add a hole inside every hole. And well, what is not as clear is that you don't have any more faces. You just have 1 other face. Okay. I'm not going to tell you exactly what this guy is, but well, basically it's a map with 1 face and p holes and some labels, and the labels have to satisfy some constraints. So rather, I'm going to explain how to go back to the map. So you start from one of these encoding objects, even if you don't know exactly what it is, and first you add inside the 1 face. Okay, so I told you that it has p holes and 1 other face. You add a vertex inside the other face, v dot here, and then you actually follow the contour of the 1 face that is not a hole, and you will connect every corner you visit to the following one with a strictly smaller label. So more precisely, if I'm here, I see a 2 here, so I will follow the contour of the face until I find a 2 minus 1, which is a 1, this one. And then I connect this corner with an extra edge. And I keep going. So here I see a 3, I'm looking for a 2. Okay, it's right here. I see a 2, I'm looking for a 1. It's this one. I'm at a 3 looking for a 2. That's the first 2. 3 looking for a 2. 2 looking for a 1. And when of course, when I'm at 1, and you can see that I didn't say it, but you can see that 1 is the minimal label of the label map. So in this case, I just connect it to the 0 here, and then I keep going. I do that until I'm done. And so if you recall Gregory's lectures, that's exactly what he did, but he started with a tree and instead of this more complicated structure. And then once you're done, you just remove the edges, and you are left with what I claim to be a quadrangulation with p holes. And if you have a good memory, you can see that this is actually exactly the same as the map we started with a couple of minutes ago. So the theorem is that this construction is actually due to, well, it's a slight modification, but it's due to Boutier Di Francesco Gitter. Tells you that this is actually a bijective encoding. Okay, so let me describe a bit more what the encoding objects are. So, well, the map itself, once again, it's just a map with 1 face and p holes. And the labels satisfy some relations. I'm not going to enter into detail. So, for example, here, this is a map you can check. It's a bit longer to check, but it has 2 holes here here and there, and one other face. So as you can see, it's not as in the previous case where the genus was 0. It was like a tree with extra holes. Here it's a bit more complicated, but if you look closely, you can actually see an underlying structure. This somehow it's the structure of cycles. It's also somehow the homotopy type of the surface. And on this underlying structure called the scheme, you have extra things. So for example, if I take this edge of the scheme here, it corresponds to this chain of edges in the map. And to this edge here is associated first some labels along this edge. So that's something I would call the Motzkin bridge, because it is a Motzkin bridge, but I didn't say what the label should satisfy, so you just have to believe me. And if you don't know what the Motzkin bridge is, it doesn't matter. And then see you have a forest on the left of this edge and another forest on the right of this edge. So every edge actually of the scheme will correspond to say a sequence of labels and a forest to the left and a forest to the right. Or maybe just one forest if you are looking at an edge boarding a hole, because there is no forest inside the hole. So it's it's always a path, some path, and one or two forests. And the forests, they have labels inside there. The vertices are labeled. Okay. So somehow there is you start from your map, you are encoded by the Boutillier-Francesco guitar bijection, you obtain something, and this thing you can further decompose it into actually simple objects. Because the scheme here, you can say that it's a finite, quite simple map. And then you have some bridges and some forests. So these are objects we can actually, we know how to grasp. So, okay, now I can explain how a Brownian surface is constructed. And that's what I'm going to do. So, is that in the discrete picture, I started from my map and I decomposed it into a collection of objects. And now I'm going to do the same, the reverse construction, but directly in the continuum. So if I want to describe the scaling limit of the map, I will actually construct the scaling limit of the encoding objects, and then I will explain how to go back to the scaling limit of the map. So first, the scheme. So that's underlying structure. The proper definition is it's actually a map, a scheme with p holes is a map with p holes, so p faces, and one extra face. And it doesn't have vertices of degree 1 or 2. And moreover, the holes are actually separated in the sense that they don't share any edges. They can share a vertex, but not. They cannot share edges. That's actually because of the construction. But I didn't explain very well the construction. So, but if you remember the face you started with, and the face you added, it actually didn't. No edges of the face you added was here, so the faces cannot see each other in that sense. Okay, and we will also say that the scheme is dominant if all its vertices are of degree exactly 3. You will see in a moment why this is why I do that. And just a remark, actually I simplified a bit the definition, because you also have to, if you want to be totally rigorous, you need to add a root edge, and it has to satisfy some a bit more complicated relations, but I don't want to go into details here. Okay, so let's just look at some example of what a scheme is. So the first example is maybe, well, of course, this doesn't make any sense in the case of the sphere, where the encoding object it's just a tree. You don't have to do anything. You don't have to decompose it into simpler objects. So the first interesting example is the example of the disk. But this somehow is quite degenerate because if you just look at the previous definition, it's empty. So you have to allow one vertex to be of degree 2. And so this is the only possible scheme. So you just have actually one loop. And so let's look at the next example, the cylinder. So the cylinder is, so you have two holes and only one face. So actually the only two possible cases is this case and this case. And if you recall, I said that this is dominant because all the vertices have degree 3. And here you have a vertex of degree 4, and that's not dominant. And the reason for the terminology is that because in the limits, things like that will not happen. So if you want, if you take a large map of the cylinder, a large quadriangulation of the cylinder, and you look at the scheme, it's more likely to be this guy than this guy. Somehow in the limit, all these guys are disappearing. That's why I say that this one is dominant. And another example, that's the same example as before. This one is a scheme of genus 1 with two holes, and it is dominant because all the vertices here have degree 1. Okay, so that's the first building block of our Brownian surfaces. And so first I'm going to recall how it works for the Brownian map. If you weren't there before, so the Brownian map is constructing like that. You first start with the CRT. So Jason just explained what the CRT was. So it's a tree encoded by a Brownian excursion. Of course, this is not a computer simulation. So that's why it's very simple. But say it's so this is your Brownian CRT, and then you put Brownian labels on the CRT. It roughly means that you put independent Brownian motions on every edge of your tree, and let me call Z this function, the same Z as in Gregor's lectures, and then you will identify the points A and B if they have the same label, and all the labels in between are larger. By in between, I mean that when I do the contour of the tree, all the labels I see after meeting this point and before meeting the second one, they are all larger. Well, of course, I could have these ones, or that could be the other way around. But if all the vertices are larger and these are the same, I will identify this point. And then I have to put a metric on this space. And I'm not going to explain how to put a metric, but so this is the space. You have this space, and with some metric. And in general, it's the same construction, but the construction is a bit more complicated. You start with your scheme, and so remember that to obtain the scheme, I actually removed the trees in the discrete picture, so I have to add them back. And so what I do, I actually graph Brownian forest on every oriented edge of this face here. And well, if you don't know what a Brownian forest is, you can just imagine that I add Brownian CRTs according to a Poisson point process on everywhere. Okay, so let's zoom in, and okay, so here it's this green thick line here was an edge of the scheme, and here you can see the trees of the forest on every side of this edge. And then you do exactly the same thing. You add Brownian labels on this structure. So here you have some conditions that, of course, when your motion goes onto a cycle, it's actually a bridge, not just a Brownian motion, but that's basically the same idea. And then you do exactly the same identification. You have 2 points. They will be identified if they have the same label, and all the labels in between are larger than their labels. And of course, there is then a metric in this space. Okay, So, right. Let me just state a couple of important properties of this structure M. So what I denote by M here is this continuous structure, the scheme with the Brownian forest. So if you want, it's the generalization of the CRT. So as for the CRT, there is a way to define a contour of this structure. So you can actually see it as a quotient of 0, 1. So for the CRT, seeing it as a quotient of 0, 1 is just what Jason explained. You have your Brownian excursion, and then so it's naturally encoded by 0, 1, right? 1. And for a more complicated a surface, you actually have to identify first all the Brownian forest, and then the floors of the forest you add on the same edge. So you have to identify this forest. It's this kind of identification, but then you actually have to identify it with the floor of the forest on the top of the edge, with the floor of the forest on the bottom of the edge. And then you also have to identify the vertices of this structure. But so it's a bit more complicated, but in the end, it's just a quotient of 0, 1. Okay. And so just a notation, I'm going to denote by M of S the point visited at time S in this structure, and the corresponding point in the Brownian surface, I will denote it by Q of S. And the first important lemma is that almost surely the labels reach their minimum only once on 0, 1. So on this structure with your labels, there's only one point with minimum label. Okay, and I will denote by S dot the instant at which you reach your minimum, and by rho dot the corresponding point in the Brownian surface. Okay, so I can now talk about some geodesics in the Brownian surface, and actually these results are a generalization of results by Jean-François Le Gall for the Brownian map. There is a famous paper in which he investigated all the geodesics starting from this point in the Brownian map, and what I'm going to say is a generalization in any Brownian surface. Okay. So for the definition, the geodesic in a compact metric space, it's a path such that the distance between the point at time S and the point at time T is just T minus S for every S and T. And we say that compact metric space is a geodesic space if every pair of points can be linked by at least one geodesic. And so the first proposition is that if you take a Brownian surface, it is a geodesic space. Somehow that's quite obvious, because that's how the metric was constructed in the discrete picture. You said that the distance between two vertices was the length of the smallest path linking them, so there is one geodesic. So if you want to be a bit more rigorous, you have to actually add all the add length 1 segments between every point in your metric space, because I said that it was just a finite metric space by considering only the vertices. So you have to add all the. You don't just consider vertices like this, but whenever there is an edge, you add a segment of length 1. So it's not very far from the finite metric space, and this is now a geodesic, because if you want to go from there to there, if there is distance 2, it means that you actually have a path of length 2. And this property actually passes to the limit, so every Brownian surface will be a geodesic space. So we'll now look at the geodesics in this space starting from this distinguished point where the labels are minimum. Okay, so first there is a very simple way to construct geodesics in a map. If you recall the embedding, I said that you started from a corner with label L, and you looked for the next one with label L-1, and you draw an arc. And if you keep going, so we'll draw an arc from the corner of label L to one with label L-1, then L-2, and so on until you reach the minimum. So that's obviously a geodesic, because the labels, I said, are the distances to this particular point. So that's a very easy way to construct a geodesic, and this geodesic will be called actually a simple geodesic. And in the continuum, these geodesics, these simple geodesics, they're still here. And well, the proper definition is this one, but I will show you a picture in a moment where it's a bit easier to see. So here, this is the function, this is the labeling function drawn onto 0, 1. So these are the labels you see when you do the contour of your structure. Or if you want, you can just think that this is the Brownian map, and these are the labels when you go around the CRT. Because what I'm explaining works also for the Brownian map, of course. So I said that there is only one point where the minimum is reached, and I denote it by S dot. And if you take any point S, and you want to look at a geodesic, the simple geodesic between this point and the point where the minimum is reached, you do exactly the same as in the discrete, but in the continuum. You always look at the next point you visit with a strictly smaller label. So you actually follow this path. You always look at the first with a strictly smaller label. And it's actually not very hard to see that a path constructed like that in the Brownian surface is a geodesic. And this is something, of course, Jean-François Lagall already did in his paper for the Brownian map. The simple geodesics are geodesics. And so the question is, are there other geodesics? And in the discrete pictures, of course, there are other geodesics. Because, okay, maybe, well, in the discrete picture, whenever you have a square and a geodesic going like that, you can also go like that, and you will still be geodesic. So in the discrete picture, somehow you have a lot of options. At every stage, you can, well, there is a lot of options, but in the continuous, of course, all the squares tend to 0, and actually these disappear. So the theorem is that all the geodesics, starting from this particular point, they are all simple geodesics. So they are all constructed in the way I just explained. And so this is the main result of Jean-François' paper in the 2010 for the Brownian map. And this is the main result of my paper in 2014. And actually, I didn't use the same method as he did, but so that's the result. Okay, so now that we know actually how all the geodesics are constructed, we can say some interesting things about these geodesics. So let's just start with a proposition. Proposition says that almost surely all the points visited by a simple geodesics, they are all leaves. Leaves in the sense that there are points that are visited only once when you do the contour of your CRT-like object. And, well, except, of course, the starting point, because the starting point can be anything. Oh, endpoint. Okay, so because that's endpoint because I said geodesic from this point. Okay. Okay, so that's a first proposition, and actually the reason why this is true is if you recall what Gregory explained for the when he showed the proof of the sphericity of the Brownian map by Jean-François Le Gal's theorem with the Moore theorem, he used this property to say that I don't know if you recall, but to say that the points are not identified both in the top half of the sphere and in the bottom half of the sphere, and that was actually one of these properties, saying that if you are identified in the top half of the sphere, you are a leaf in the bottom half of the sphere. If you remember that proof. If you don't, it's there is a way to show it. And that's the same kind of a method. Okay, and well, so now that my surface is not necessarily a sphere, there is an interesting thing to look at is that the geodesics. Okay, so you can have points where it's possible to find points such that there are two geodesics going to this rho dot guy, and okay, so you will see that actually they will merge, but whatever. So when these guys, if you look at the points such that there are two geodesics, and maybe they will exist, you can look at the loop, this loop. And so if you are in the Brownian map, this loop is a loop in the sphere, so it will be homotopic to 0. It will be contractible. But in a general surface, it can be contractible or it can not be contractible. So we can look at points such that this loop is actually not contractible. And that's what I'm going to do now. And the proposition is actually the following. It's there is a pretty easy criterion telling you whether this happens or not. And the criterion is the following one. When you do your contour of your structure, CRT structure, at each stage you are inside some forest, and so if it's time s, you will denote by ES the oriented edge of the structure containing this forest. And the theorem is that actually the path, this loop, if this is time s, this is time s and this is time t, and you want s and t to encode the same point in the Brownian surface, well, the theorem is that the path is homotopic to 0 if and only if you are actually in the same forest. So on a picture, it looks like that. So here you have your rho dot point, and you take a point. So okay, I didn't draw all the forest because otherwise it would be too messy. But imagine that you have Brownian CRTs grafted everywhere on this structure, and you take a point here, which will be visited at some instant, an instant s, when you do the contour, and well, maybe another instant t here. But here, the forest you are in at instant s is the forest on the top of this edge, right? And at instant t, you are actually visiting this forest, the forest on the bottom. So these are not the same forest. And the proposition says that then in this case, the simple geodesic starting from this point and the simple geodesic, I would more say, starting at this instant, form a loop that is not homotopic to 0. And actually, if you recall that all the simple geodesic visit only leaves, they cannot cross actually this structure, and somehow that's the only possible a way to merge. They have to do a loop that is not homotopic to 0. Another example, if you look at this point here, and so you visit it at some time s prime, then you go into a tree, and then when you go out of the tree, it's time t prime. So you visit this point twice. Then in this case, your two geodesics will form a loop that will be contractible. Okay, so knowing this simple proposition allows you to compute some very nice quantities. For example, let me call n the set of points satisfying this property that there are two paths such that forming a loop that is not homotopic to 0. Two geodesics forming a loop not homotopic to 0. Well, from the previous picture, this set just corresponds to the green edges here. That's the only point that will be actually visited from two different forests because, well, that's where the forests are glued. So the green edges here are exactly the points satisfying this property. And then we can compute, for example, the Hausdorff dimension of this space. And it is almost surely equal to 2. And well, that's actually exactly the same proof as to for proving that the Hausdorff dimension of the boundary is 2. It's because somehow the boundary are the Hausdorff of the boundary components are the Hausdorff dimension of the loops here, and the Hausdorff dimension of the set I'm considering is the Hausdorff dimension of the green edges here. But actually, every edge will have Hausdorff dimension 2. So that's the same dimension. And well, you can also ask the following question: how many geodesics are there between a point, any point, and your base point rho dot? And the theorem is that, well, you can actually read that directly on the CRT or on the structure N. And the answer is just the number of connected components of this structure with some, well, I will explain the other terms here. So in particular, if you know that the CRT it's a binary tree, this number is at most 3. And if you take a typical point in the Brownian surface, there will be only one geodesic between this point and the distinguished point. Well, then actually, there is some invariance on the rerouting on the surface, and you can actually replace this point by a uniformly chosen point in the surface. So if you take 2 points uniformly at random, there will be only one geodesic between these 2 points. That's something stated here. And okay, on the picture it will be clearer here again. So this is a part of your still your CRT-like object. And let's look at the point here. If this is a leaf, in the sense that well, you will visit it only once, there will be only one geodesic starting from it. If you take a point here, you will visit it twice, and there will be 2 geodesics starting from it. And remember that they will actually form a loop homotopic to 0 because they are visited, you are still in the same forest. If you take this point, for example, you will have 3 geodesics, and there are no points with more than 3 connected components in the neighborhood. So that's the most you can do. And so you can also take points like this. On the scheme and with the tree, you would have 3 distinct geodesics. And these 2 here will actually meet, forming a topological disk, whereas this one and this one, for example, they will meet while doing a loop not homotopic to 0. And you can also look at points on the boundary. Well, the boundary is a bit different because you don't visit it from the inside, so you only have one geodesic starting from this point. So that was there was a -1 if you are on the boundary in the previous slide. Or you can also have points on the boundary that where there is a tree, so you will actually have 2 distinct geodesics starting from this point. So actually, if you are on the boundary, you can never have more than 2 such geodesics.
Suppose you take 2 points which are on the boundary of the loop of the loop. So
and you want to look at the geodesic between these 2 points.
Yes.
That I don't know how to do, because typically well, I can only look at geodesics aiming to that special point rho dot, which you can replace by a uniformly chosen point. But if you take a uniformly chosen point, it will not be on the boundary. It will be a leaf in this structure. Okay? And so let me just finish by looking at even more peculiar points. The point, so I told you that there is at most 3 distinguished geodesics. And we looked at the points for which there exist 2 different geodesics forming a loop not homotopic to 0. And we can also look at the points where you have 3 distinct geodesics, and such that every pair of geodesics you take will make a loop that is not homotopic to 0. So you have these guys, and you have also points. Well, you could have points where you have 3 geodesics, always aiming at the same dot. And you can look at the points such that this loop is not homotopic to 0, but this loop is also not homotopic to 0, and of course the other one will have the same property. And these points, well, there is actually a finite number of such points. And well, we can compute the number of such points. Well, of course, if you look at the sphere or the disk, you don't have any points like this, so that's not interesting. But if you look at another structure, for example, without any hole, the torus of genus G, you will have a finite deterministic number of such points, 4G minus 2. For example, in the torus, you have 2 points, exactly 2 points, having that property. And if you have boundaries, you actually get a random variable. But the counterpart of this variable is the points on the boundary such that you satisfy this property. If you are on the boundary, you can have at most 2 geodesics, and you can ask whether these geodesics form a loop not homotopic to 0 or homotopic to 0. And actually, the theorem says that if you take the points like this one, and you add the points like this one on the boundary, you also have a finite deterministic number of such points. It's 4G plus P minus 2. And some will have this property, and some will have this property. And so why is that? So this is because these points, they actually correspond to the vertices of this structure. Because, well, it's actually a point that has to belong to 3 different forests. So if you belong to 3 different forests, it means that you are a merging point like this. And here you have 3 geodesics, and here you are not in the same forest as here, and here you are not in the same forest as here. So they will, every pair will make a loop not homotopic to 0. And on the boundary, for example, this one, you only have twice, 2, and you have these 2 geodesics like this. Okay, so let me just finish by mentioning the reason why I draw the picture like this is the famous property of confluence of geodesics that Jean-François Le Gall observed in the Brownian map. Well, it says that if you take your point, I don't have any more here. If you take your point rho dot here, and you take some epsilon here, well, you can always find a small eta here, such that all the geodesics starting from outside of this ball, they will all merge before entering this small ball here. That's a property that says that somehow every Brownian surface has some very thin peaks. That's what you could see on the picture. And I will just finish by showing you other computer simulation of totally random maps.
Question.
horse. So you said the boundary of the horse is not necessarily
Yes.
but in the limit.
Yes.
It is. Okay.
Yes.
So
What was the question?
So in the discrete picture, I didn't ask the boundary of the holes to be a simple curve, but Jean-François said that in the limit, as the topology is the topology of the surface with the boundary, in the limit it becomes a simple curve. So that's so this wasn't a question.
I just wanted to check with you.
Okay, so yes, the answer is yes. That is totally right. So in the limit, somehow you have this. If you take a hole, in the discrete picture, it can have all things like that. But in the limit, all these trees or small maps they will all disappear, and in the limit, you will have a simple curve. That's right. Yes.
In the construction, you had a Motzkin bridge, or in the continuum version,
Yes.
Brownian bridge, I guess, on the edges of the scheme. So they must have lengths.
Yes.
Are the lengths determined by the sigma, or are they random?
Yes. The length of the. Okay. So you have. So you have this, maybe, I think blue is bad. So you have the holes, okay? And you have the other connecting edges. So for example, this one will work, okay? So of course, the total length of this, so if this is, say, H1 and this is H2, the total length of this loop here will be the sigma 1 infinity, and the total length of this one will be the sigma 2 infinity, right? The total length, but the other length, there will be random variables, and we can actually compute the distribution of this length, because there is of course a complicated conditioning to consider. But so you first actually sample this map according to some distribution, to some limiting distribution, and you also sample the length of every edge of this map, and you also sample the labels of every vertex of this map, and then conditionally given that, you sample Brownian bridges and Brownian forests and everything. And yeah.
One more?
So, although you have very rough metrics, is it possible to make sense somehow of what the conformal structure would be? For example, if you have a Brownian cylinder, can you define a random variable which would be, the
The
modulus?
conformal, yeah. I have no idea how to do that.
Well, let's thank Jeremie again.
Sorry.
We have a tea break now.